India faces a perplexing climatic paradox. News reports are filled with images of scorching heat waves, melting roads, and overwhelmed hospitals. The summer of 2024 was etched in India's history as the hottest on record, with temperatures soaring to unprecedented heights. The human cost of this extreme heat was devastating, with hundreds of fatalities reported during the relentless heatwave spells. Despite these tangible signs of a warming climate, India's overall warming trend tells a different story. Since the beginning of the 20th century, India's average annual temperature has risen by less than 0.7 degrees Celsius. This figure stands in stark contrast to the global average, which is closer to 1.4 degrees Celsius over the same period. The question arises, why is India seemingly lagging behind in the global warming race, even as its people bear the brunt of brutal heat waves? This unexpected trend has become a focal point for climate scientists and policymakers alike. At a recent climate change conference in New Delhi, jointly organized by the Indian Environment Ministry and Harvard University, the issue took center stage. Researchers presented various hypotheses, each attempting to unravel the complexities behind India's unusual warming pattern. One prevailing theory points to the role of air pollution, a well-known problem plaguing many Indian cities. The argument suggests that high levels of air pollution, particularly aerosols, might be reflecting sunlight back into space, creating a localized cooling effect. However, the science behind this theory is not straightforward. While some aerosols have a cooling effect, others, like black carbon or soot, can absorb heat, potentially contributing to warming. India's struggle with air pollution is well documented. Major cities frequently rank among the most polluted globally, with air quality reaching hazardous levels, particularly during the winter months. This pollution, primarily a byproduct of industrial emissions, vehicular exhaust and agricultural burning, hangs heavy in the air, forming a thick blanket of smog. While detrimental to human health, this smog has inadvertently created a complex interplay of forces within the larger climate system. Aerosols, tiny particles suspended in the air, are central to this phenomenon. Their behavior in the atmosphere is multifaceted and depends on their composition. Sulfate aerosols, for example, tend to reflect sunlight away from Earth, contributing to a cooling effect. This cooling effect is believed to be particularly pronounced in regions with high sulfate aerosol concentrations, such as India. However, the pollution paradox arises from the presence of other aerosols, notably black carbon, also known as soot. Unlike sulfate aerosols, black carbon absorbs sunlight, leading to localized warming. Given India's reliance on coal-fired power plants and the prevalence of biomass burning, black carbon emissions are significant, potentially counteracting the cooling effect of sulfate aerosols. The net effect of these opposing forces remains a topic of ongoing research. Scientists are working to quantify the relative contributions of different aerosol types to India's overall warming trend. Understanding this complex interplay is crucial for developing effective climate policies, as addressing pollution through measures like reducing coal dependence could have unintended consequences for warming rates. Beyond the pollution paradox, another intriguing theory focuses on the impact of India's extensive irrigation network. India is one of the world's largest consumers of water for agricultural purposes, with vast swathes of land irrigated to support its massive population. This reliance on irrigation, while essential for food security, might be playing a role in mitigating warming trends. The crux of this theory lies in the process of evapotranspiration. When water is drawn from the ground for irrigation and then evaporates from the soil or transpires from plants, it absorbs heat from the surrounding environment. This absorption of heat, known as latent heat flux, effectively cools the air, similar to how sweating cools the human body. A 2020 study published in Science Insider provided evidence supporting this hypothesis. The study found that expanded irrigation practices throughout the 20th century had a noticeable dampening effect on global warming, particularly in South Asia, including India. The researchers concluded that irrigation played a significant role in offsetting some of the warming caused by greenhouse gas emissions. However, the cooling effect of irrigation is not a long-term solution. As climate change intensifies, leading to more frequent and severe heat waves and droughts, the demand for irrigation is expected to rise, further straining water resources. This could create a vicious cycle where increased irrigation, while providing temporary relief from heat, exacerbates water stress and potentially diminishes its cooling effect over time. Section 4. Shifting winds, a climate in transition. Adding another layer of complexity to India's climate puzzle are the changing wind patterns influenced by the rapid warming in the Middle East. The Middle East, already one of the hottest and driest regions on Earth, is experiencing a faster rate of warming compared to the global average. This accelerated warming is altering atmospheric circulation patterns, impacting monsoon systems and wind flows across the region. A 2023 study, published in Science Insider, investigated the link between Middle East warming and monsoon shifts. The researchers found that as the Middle East warms, it creates a pressure gradient, altering the traditional northward trajectory of monsoon winds. This shift in wind patterns results in increased rainfall in Pakistan and northwestern India, potentially contributing to devastating floods in recent years. While this study focused on precipitation changes, the implications for temperature are significant. The altered wind patterns could be influencing the distribution of heat across the region. For instance, stronger winds carrying moisture from the Arabian Sea might be contributing to increased cloud cover and rainfall in certain parts of India, potentially masking some of the warming signals. Furthermore, the changing wind patterns could be influencing ocean currents and heat exchange between the ocean and atmosphere, further impacting temperature trends. These complex interactions between atmospheric circulation, ocean currents, and regional warming